Okay, so to start, and Anthony Wood said it this morning that form should be influenced by its height. So this diagram shows, three birds. Of course, their form uniquely suited for the habitat, or specifically the elevation of its habitat at which it dwells. So while not even Dennis Poon can get an ostrich to fly, okay, or a penguin to run as fast as an ostrich, although he might try. Because certainly he's one of the hardest working professionals in our industry. Could you do it, Dennis?
Yes.
But it might cost the client.
We can negotiate that later.
Okay, so architecture and structure. So while on stage, Dennis and I might be very different sizes, on screen you can see our work is very closely aligned. Now for more than any other building type, the tall building structure and architecture are inseparable. And it's not a question of passing the baton, the architect handing over the design to the engineer, but it's one of constant back and forth collaboration. Hopefully these can run. Let's see. You mind clicking on the boxes? There we go. Yeah. Okay, this is the Chinese martial arts, Tway Shou. So I thought it was a nice representation of the dynamic between architect and engineer, but also it represents a very important aspect of Chinese philosophy, which is not to resist force with force, but to yield to it, to misdirect the force, and then to redirect it. And I thought that was a very nice analogy to how engineers design the structures of tall buildings. Because the Chinese have understood for thousands of years, they have expressed the physical world in terms of energy. And I think only now, a lot of people at this conference were talking about the embodied energy of buildings, which Dennis will elaborate on, but the idea that there is a certain amount of energy that's inherent in the form. Okay, this being a very important project for KPF and for myself, personally having worked on it, but the idea that the building doesn't resist the wind head-on, but yields to it, or more specifically, just allow it to pass through. The moon gate at the top, which was controversial, because it looked like, and this is not supposed to be the Japanese flag either, but this is a sphere. The sphere representing the most compact volume in nature. So the ratio of the volume to its surface area is the most compact, and a lot of other forms might be compared to the sphere, and it's called sphericity, like how much does it deviate from perfect compactness. So when we look at the Shanghai Financial Center as a benchmark relative to Ping An, you can see the strategy here is to make the building as compact as possible. So it's as if the volumes or the spaces that weren't needed were simply carved away out of the building. So the building transforms from office at its base, tapers back to hotel towards the top, and then finally at the observation deck, where pretty much you only need window frontage, it transforms into a line. So the idea that the transformation of the mass coheres to the transformation of the internal space is very important from the point of view understanding that we're not wasting space. So we're not raising volume up into the air that would in turn take on more wind. Okay, and then of course another notion is that the architecture and the structure should be in perfect alignment, that these two things should adhere to each other, and should they deviate is where you get a waste or you get a loss of energy. Okay, so coherence and adherence. So the idea that the internal, the form, the function, and the structure should be in perfect phase with each other, and where they are not is where you get a waste. Okay, which brings us to Ping An. So here you see an image of the project seemingly rising out of nowhere. And actually on the left side of the image, the mountain is in Hong Kong, and on the right side, the mountain is in mainland China. Okay, so to understand the project, I think we should talk a little bit about Shenzhen and its context. So Shenzhen, unlike most large Chinese cities, it doesn't have a history. It's not a traditional city. It was a village up until about 30 years ago, and then exploded because of its proximity to Hong Kong. So you can see on the diagrams on the left, the river is the border between Hong Kong and mainland China, and the city has developed from east to west, strung along the border. This building also only makes sense when you understand it in context, not just of Shenzhen, but the entire Pearl River. So this diagram shows the connectivity of this tower to Hong Kong via the XRL, which is the new high-speed rail link that will go from ICC in Kowloon to this project in 14 minutes, which is probably faster than it takes to go from Pudong to Puxi. And incidentally, you take the train another 30 minutes and you're at Chris Wilkinson's project in Guangzhou. So the idea of these towers, they're not sprouting out at random, but it's part of the infrastructure of the entire Pearl River Delta region. So here's a view of that. The green line that cuts through north-south, that's the XRL rail link. You can see towards the bottom is Ping An. And then you image now of the tower growing out of that infrastructure. And I think only when you see the tower in these terms, it begins to make sense. Okay, now the image or the brief of the project, the client asked us to do a couple things. One is that the tower form had to represent the stability and the solidity of their status as an insurance company. The second was that they wanted the form to express the spirit of Shenzhen. So Shenzhen, like I said, is not a historical city, but a city that was formed by immigrants coming all over from China, different ethnic groups, different languages coming together to build something great. So the idea of lifting up the ground, so the notion of pulling the ground up, and then the form of the building taking the path of least resistance, like the Tway Shou, the least resistance. So the form of the building becomes an expression of kind of the material consistency of the building pulled down by gravity. And actually, when we were working on the project and designing it in Rhino, a lot of times we actually modeled it upside down to try to reinforce these lines, to reinforce the idea of the folding of the building from top to bottom. And then here you can see imagery of the project. So it's clad with these stainless steel strands, again, to emphasize this tug between the point in the sky and its weight at the base. So this idea of a very ductile tower that's been stretched. And then here at the base, so you get the feeling of a great weight at the bottom of the tower. You can see the 8 mega columns coming down. Dennis will explain the structure at the corner, which arches down to create a large gateway at the bottom. So we only have 8 points of structure that come down at the base, allowing a great deal of transparency through the building. Okay, and then images of the podium. Again, the idea of the ground swelling up to grab the tower. Okay, so there it is, the final form. So it feels extremely delicate, as if just poised in equilibrium between the ground and a point in the sky. Okay, so getting back to the form and what makes the form appropriate for its height. So here's an image of the tunnel of the project in the wind tunnel test. Now there's a couple of very important things that were done. While the tower is more or less straight up and down, purely vertical for most of its height, the corner is recessed and the corner is continuously tapered. And by doing that, we're able to reduce overturning and wind load by over 30%. Okay, here's a typical floor plan. This is at the zone 2 of the building. So it's 8 mega columns, concrete core. This is one of the important moments of the project for me, was when actually Dennis came back and said we figured out we needed to have a certain dimension from the front of the column to the center line of the trusses, and one could have done two things, which was pull the truss inboard, which would have wasted space, but sort of that Tway Shou moment was actually deciding, why not let's just push the columns outboard and break the plane of the facade. And actually that had enormous aesthetic implications, but actually in a very positive way. And we wouldn't have thought about it unless we were listening to our engineer. Okay, so here you get the idea of the adhesion, so the structure sticking very closely to the face of the building. Okay, and then at the top of the building, you can see the transformation of the corners. So at the very top, we also bevel it, so the floor plate, in the perspective of the wind, is going to look like a circle. So the idea of a rounded floor that performs much better at the high wind speeds. Okay, and then the transformation of the core as well. So as one manipulates the form for the wind, one also needs to think of its impact on the core. So the entire organization of the core transforms from a square to a cruciform, so that we eliminate that pinch point when we have to bevel the corners at the top. Okay, and finally, to get to the top of the building, so there's a spire at the top. So the spire was kind of vexing for me because it doesn't quite fit into the story of the sustainability and the minimizing of the embodied energy, but it's very difficult to resolve this form without a spire. It seemed like to be the only natural way to resolve the form. And it generates complexities because of the galloping effect of the spire as it's blown by the wind. So what we're looking at now as a team, and this is still ongoing, is to actually look at opening up the spire. So rather than a solid spire, it's a hollow spire. So again, rather than resisting the force of the wind, simply to let the wind pass through. Okay, and then finally, just to conclude a little bit on why go this tall. I think ultimately it's because we all enjoy it. As people, we enjoy going up to the tops of these buildings, and we work with the client to convince them to open up the top of the building to the public. So here you can see a cutaway view of the dome. Is a great cathedral-like space for observation and restaurants. Okay, and finally at the end, just the image is all about the people and the participation, the thrill of being at the top of a tall building. So images of my team sort of hanging outside the building with these glass bay windows over the cascade of the building face. So this participating in the tall building is what makes it truly enjoyable. And with that, I'll hand it over to Dennis.
Thank you, David. Good morning, dear friends, colleagues, and my boss, Richard Tomasetti here. I'm glad to be here to share our design experience of this super high-rise building with KPF's designer, David Malott. It has been a very pleasing process because, as David has emphasized, the whole design process is very much a close teamwork with each other, and also with the owner's project director, Mr. Lau Dai Chen from Ping An. He's here today. They pay attention to every aspect. Because if I'm here to talk about all the engineering and all that, I mean, a lot of you here, being expert and experienced people in the field, should know already how to design the building. But I want to emphasize today how every process will be enhanced with a better result with the teamwork working together so that we can move on to design another better project and emphasizing the tricks behind it, not necessarily the engineering expertise. Again, this project is very much governed by several major factors. One, we're into the 21st century high-rise design. Everyone knows how to design a tall building. Everyone claims that they know how to use the software. But the goal is not knowing how to use the tools. The goal is to meet the target set by the owner, which is very much the sustainable design aspect of this project. So with this in mind, we set out to work together on every aspect. One is how to achieve the optimum design from the structural part first, together with architects. So we have the carbon reduction goal. And in the nowadays sustainable design, we talk about two major elements. One is the embodied energy, and the other one is embodied carbon. When you use certain products or manufacture certain products, you use a lot of fuel oils to manufacture this product. And the byproduct of this manufacturing is causing a lot of carbon emission into the atmosphere. So we try to limit this carbon emission. And that's why we try to use the right material And also we have to limit its transportation, its manufacturing costs, because each one will contribute to the environment. Okay, you can see nowadays, what is contributing to our carbon emission, it is in different areas. Now, when we design the building, it uses up so much basic energy because when you use a lot of steel, it consumes so much energy. When you use so much concrete, you also consume fuel. But after that, you're talking about the building operation, just like Mr. Job, the owner before. It costs millions of dollars to operate a building with mechanical system and operating system. So we have to pay attention to all of that. Structurally, the envelope percentage, you talk about almost 28% of the embodied energy, site work, construction, finish, and structure accounts for 21. So we have to pay attention to every aspect. And during the design process, we go through this together with the entire team. Now you can see the energy cost. If you use aluminum, it will cost this kind of energy. Steel is the second culprit. You use so much. PVC, and then if you use cement, you can see with cement, you use a lot, you have better environmental impact. And cement is is much cheaper in China, and the labor cost is cheaper. So we try to strike a balance in the selection of materials. Now, for this project, eventually, after months of work together as a team, we have to use the most efficient material, and durability, adaptability, deconstruction, and so on. Foundation is a challenge, okay? The site is very, very tight, so we cannot have a large mat. So we have to deal with foundation, then the superstructure has to deal with architectural requirements, and then the facade. To summarize it generally, we try to have about deep foundation with ball pile all the way down to the weather rock. And the pile is supported by the mat. The mat is supported by the piles. Okay, we have the hand-dug caissons, and on top of that, we have a thick pile about. Now, this is a layout, and we try to use big diameter ball pile in order to spread the load. And it saves a lot of labor by using deep ball piles and large diameter all the way down to rock. In the podium, we are using the regular smaller piles system. So what you see is a very simple outcome of engineering with a lot of analysis get into it with the optimized design. And we study all kinds of behavior of the mat foundation, including the base rotations and so on, and flexibility and the spring constant. All kinds of engineering were built into it to make sure we have the most optimum design, not to waste any construction material. Now the building is separated in different zones, and the structural system is mainly a concrete core, composite concrete core, working with outriggers, and also a mega frame outside formed by the belt truss. And in addition to that, we have a secondary diagonal bracing to enhance the stiffness for earthquake, the stiffness of the building during earthquake as a secondary system. Well, the main thing is architecture and structure to be in harmony. Every step along the way of engineering, we get to work with the architect, as David has pointed out. So the location of each outrigger truss has been carefully studied with numerous options when we come to this final design. We have done a lot of three-dimensional analysis and with beam modeling as well as 3D analysis, which enhances the optimization process with the architect and mechanical engineers. At the end, you can see and do what a simple engineering product and architectural layout it will achieve. And if you look at the lateral system, we have the core. This is the mega frame form outside, conveniently located at the mechanical levels, and then we have all these diagonal truss. Even the truss configuration has to be worked out in a simplified way to fit the architecture in order to minimize the obstruction of view for this super tower. Now, the concept of using an outrigger and a core is very simple. The core itself is not stiff enough for a 660-meter tall building. Just like when you try to bend a pencil, it's not stiff enough. But if you try to bend a pipe, it's much more stiffer when you try to bend a pipe. So we work out the outrigger system. And with the bell truss. The bell truss is forming the mega frame outside the building, which forms like a frame for the secondary system. This is the mega brace. Well, people will ask, why you need a mega brace? Because is your core stiff enough? Is your bracing stiff enough? We have to deal with the China code. This is something that we can discuss later. Now, different codes have their own provision, and different location of the project will have their own projection. For this, in order to meet the seismic requirements and the wind load that we have to deal with, we have to introduce this mega frame. Shenzhen is located north of Hong Kong, which is subject to very high wind load. And if we make the core too big, to make it stiffer, it will decrease the efficiency of the floor plate. So we are working with the architect and come out with a solution to have this mega frame and this mega bracing. Now, the structural system will be kept as simple as possible. Basically, we have a core. We try to line up the outrigger system so that we utilize the whole width of the building in each direction in a very symmetrical way to receive overturning, the wind load, and seismic load. Now, in addition to that, we have a bell truss at the mechanical level every 14 to 15 story. And this bell truss is about 2 story deep that forms the mega frame in addition to the very lightweight mega frame system. Now, you can see, as David said, we try to push out the mega column, which again, we use a lot of concrete to reduce the carbon footprint. And we try to use high-strength steel to save the material. And then with this working together, we have a very efficient structure and low tonnage. But along the way, we went through many obstacles about how to meet the optimum design. So we have to perform a lot of in-depth analysis, working with the experts in order to come up with this design. This is the core with the link beam. And in some places, we have embedded steel plates to enhance the strength of the core. Again, you know, structural optimization is being done in every step of the way. We also have to look at simplicity of construction. So when we do the detailing of the steel and the structure, we have to bear in mind how to make it simple for steel erection and coordinate with mechanical engineers. You can see this may be a lot of typical design principle that every one of you will know how to do it. But when you go through the process, the amount of depth of work is different from each project. So with the core, with the mega bracing, with the outrigger, the mega frame, we have successfully designed this building that works for architecture with the function requirements set by Ping An Insurance Company. Again, we have to deal with earthquake. Shenzhen is 7-degree earthquake, so we have to deal with that also on the dynamic aspect. So seismic design is another important design criteria in China that we have to deal with. And we have to do nonlinear analysis, performance-based design for optimization, that everybody think that, yes, I know how to do it. But this time we are working with the experts in China. We do site-specific analysis. We do a lot of geotechnical testing. We work with the expert on coming up with the most appropriate seismic curves for this project in order to do the correct, most appropriate earthquake design for this project. So we had to emphasize that you cannot apply what you have done on the previous job and then on the other job, except with your experience. So the design criteria can be different on each project. Now again, we went through a lot of work with KPF and David on the geometry of the building, amount of tapering of the building as it goes up. How do we treat the corner? How do we treat the corner of this building? How do we taper it to reduce wind load, and working with the wind tunnel engineer? On the other aspect of the design, we have other contribution design for the sustainable design, such as natural ventilation. We have heat recovery system. We have high performance facade. We have ice storage, and we have occupancy light control. So you can see a whole series of sustainable design engineering have been built into the project. Thank you.